ladies and gentlemen. Welcome to Basel 1. Welcome to rock-solid JavaScript through applied science. My name is Dierk Ko. I'm working for Karakun, just around the corner. Your preferred IT provider, I guess, as so-called fellow, which means I'm not bound into the day-to-day business of writing software so much in that occasion, but I do lots of consulting and training and so on. I also work as a professor for computer science at the University of Applied Sciences and Arts, Northwestern Switzerland. And this talk, since it has applied science in the title, you can expect to give you some feeling of university, right? Like seeing a blackboard, smelling the chalk, sitting in uncomfortable chairs. Yeah. You get the feeling. If you already feel uncomfortable, that's on purpose. Yeah. By the way, I have no problem whatsoever if my friends in the industry call me the academic, as long as my friends in academia call me the practitioner, then I'm fine. You can find my Twitter handle, the personal one and the more official one from university, and also my homepage. Just there, and everything that I talk about today is in one way or the other linked from my homepage. Since we talk about JavaScript, who is working with JavaScript? Writing some JavaScript on occasion, like pretty much almost everybody? Thank you. Who received any kind of formal training in JavaScript? 1, 1.5? Okay, that's typical. It's usually below 10% what I get as a feedback. So, as a software developer, you're supposed that you know how to write JavaScript because that's so easy. Everybody knows how to do it. So, a software developer, of course, know how to write JavaScript. And good one, and working one, well, without having any training. So that's kind of an unrealistic expectation. We will take the opportunity today to raise the bar just a little. You'll see. Now, the title says, Rock-Solid JavaScript Through Applied Science. This is an oxymoron in two ways. First, JavaScript is not supposed to be rock solid. It's supposed to be a house of cards that with every small wind that blows, then everything falls apart. It doesn't work in my browser, it gives me undefined is not a function, and so on. Who has ever seen undefined is not a function? Everybody, thank you. Okay. Second, when you think about JavaScript, you don't think about computer science because, you know, the science, academia, and computer science, by the way, if you have a science that needs to stress that it is science by putting science in the name, your claim to be science is somewhat suspicious, you know. Physics doesn't have science in physics, but we do. So because it's somewhat questionable what we do anyways in terms of real science. And then when we do science, we want to have stuff that is, you know, at least as good as Haskell, or maybe even Scala or so. But yeah, it must be type system whatsoever, and linear types, and whatever types, yeah. But it turns out that the very foundations of computer science can be nicely taught with JavaScript, and pretty much everything that is in JavaScript relates to the foundation of computer science. And we will experience that to some degree today. So let's see. By the way, oxymoron has the word moron in it, which means jackass or something like a dumb person. And oxy, like an oxygen, means ultra sharp. You know, the word means ultra sharp and dumb in one word. which of this is ultra sharp and which is dumb. Your choice. So let's see what we can do. At the very foundations of computer science, and if you've been to university or that kind of training, you learn this in theoretische Informatik at the very beginning. That is, at the very root is the idea of what in the world is computable to begin with. And this question was open for at least 2,000 years. And then 3 people came at once on very similar ideas. Pretty much everybody knows Alan Turing and the Turing machine. That's what you learn, right? The Turing machine as a theoretical device, not as a practical device, as a theoretical device, as an idea on how you can compute something, has been very successful, and you learn this everywhere, but there is very limited actual application of a Turing machine in code. Actually, if you want to teach this, it's difficult, right? Because building a Turing machine is not so difficult, but letting it do something useful is difficult, since it is so low level. And then came a second one, Alonzo Church, this guy over here, and he was actually the professor of Alan Turing. Alan Turing was his PhD student. And he invented the Lambda Calculus, which turns out to have the exact same computability characteristics as the Turing machine. Whatever you can compute in the Turing machine, you can compute in the Lambda Calculus, and vice versa. And what you cannot compute the other way. And then there also was a third one, lesser known, but also interesting. Kurt Gödel produced something called recursive functions, which again has the same power in terms of computability. So for today, we will not use the Turing machine. We will go with the Lambda Calculus and apply the Lambda Calculus to JavaScript. Don't be afraid about the words. Lambda is just a letter. We could have called it the L calculus instead of lambda. So it's just a Greek letter. There's nothing behind it. Second, calculus has nothing to do with mathematics. It's just a way of reasoning. We will go through the rules of the Lambda Calculus, what is allowed in this kind of reasoning. And that's it. And there's only 3 rules so it's only a few rules, let's put it that way. I should not say it's easy because, well, my students never like it when I say something's easy. Good. Here we come. Here we go. The Lambda Calculus has 3 operations. First, it has a special kind of notation, but I'm not going into the notation. I will use JavaScript notation for this, right? But it has 3 operations. You can rename a parameter. Just like when you have a function, you can rename parameter refactoring if you want. This is just renaming stuff which is in your current scope. Then there's a beta reduction and beta expansion, mostly reduction, which means you have a function and you're applying an argument to the function. You're calling the function with an argument. And then there's a special way that you can cancel out parameters if you don't need them. We'll look into this in a second. So that's all there is. It doesn't know anything about numbers or strings or not even functions. It's just a notation. You know, it's like you can actually work with this on paper and calculate. So how does it look like alpha, beta, and eta? Alpha translation, and this is JavaScript notation, is you do have an x. These are your formal parameters. You only have one. And here is what you do with it. You just return the x, for example, the ID function. What's not in the Lambda calculus, but what we will use is we can give this construction a name, and we give it the name ID. That's it. That's all there is. This is the fat arrow notation for lambda expressions, fat arrow functions in JavaScript. That's it. So alpha translation means you can just rename these parameters, and then you have to find all the matching parameters on the right-hand side, and you just rename. Simple enough? Give me some nodding. Thank you. Good. Now, applying a function, beta reduction, is a little bit more involved. Here it comes. We do have, we're using parentheses for just visual grouping. You don't actually need them in the Lambda Calculus, but makes things easier. So let's say you do have a function here. That's a function with a formal parameter and something on the right-hand side. We don't know yet, we don't understand yet what that is. You do have a function, and the function will be called with some argument. We forget the other part for the moment. What do we do when we do a function calling? Well, we take this argument, we pass it over to the f, then we remove the f and we remove this argument, and we replace all occurrences of f in here, just, letter by letter, through what has been passed in, right? So now the f must be replaced by id, and you see this over here. We remove the f, we remove the id. That's what you do in your head when you're reading JavaScript code anyway. So that's how you pass in a parameter. Now, the return value that this evaluates to, it's actually a full equivalence. Both terms here are fully equivalent. It's an equivalence translation, like in algebra, because it is an algebra, as we will see. Okay. Here's a second one, another function and another argument. So, same chore, right? We take it, put the x in, take the one wherever the x is, there, and the x goes away, and ID1 comes in. ID1, we can actually expand the ID. We have created ID on the first slide as x to x. We put this in here instead of the ID. Then we can pass in the ID, and we get a 1. Every single line on the slide is fully equivalent to all the other lines. There is no difference between them. It's equational reasoning. Clear so far? Good. You're all practitioners. You have seen so many function calls. You say, well, get on, get on, get on. I want to see the beef. Yeah, good. And now comes eta. Eta, the last operation, is actually a little bit surprising, but cool. So if you have a function, this is a function which has a parameter and whatever body. Now this function evaluates to, it returns, we say, a function, exactly. So it returns a function that does something with x and y. X and y is known, it's bound. It's a bound variable. It's there. It's calling plus with x and y. Now, the rules of eta reduction is that if you have on the right-hand side a very last argument, which refers to the very last parameter in this list of appliances, then you can cancel them out. Exactly as in mathematics, when you have multiplication and you're canceling out the multiplication on both sides. Like divide by y, kürzen in German, right? You're canceling out the y. So y and y, remember, eta reduction, we're going to use it. Eta reduction, you remove the y. And we are left over with plus x, and the last parameter on the left-hand side is also an x. So we can cancel it out. What stays is plus. And all 3 lines are fully equivalent. In any piece of code, you can either write this, or you can write this, or you can write this. It's fully equivalent. Make sense so far? You might say, well, obviously, this is the plus function. It is plus of x and y. And you can write it as with all the parameters, or you can just refer to it by its name, plus. I'd say it makes total sense, right? So these are the steps that we can do. Those are the steps that are at our disposal. Here we go. What do we do next? Well, we are creating a few functions, and actually, you only need 3 functions, and not these 3, but very small functions, and then by combining the functions, you can compute everything that is computable in the Lambda calculus. You only need 3. The identity, the constant, and the so-called the S combinator. So, but we will start with the simpler one. We first create for ourselves, as a building block that we will use, the ID function, x to x. And we make a second function called FST, means first, but for historic reasons, I call it FST, which is a function that first takes an argument and returns a function that takes a second argument, which, when called, returns what has been passed as the first argument. It's also the constant function. It's also the true function. Anyway, so for those that have seen it before. So that's from x and y, it's the first one. Not surprising, huh? And if you have a first one from 2, well, you might have a second one as well, and this is what you see here. And this is fully valid JavaScript code, and that's fully valid Lambda Calculus in JavaScript notation. These are the terms that we start with. Now, how can we possibly make this useful for something? Well, we could produce a class, an object, a constructor, if you may, which we call it pair, which takes an x and takes a y and a third one. We call it accessor for the moment. And when called with all 3, it will apply the accessor is since accessor has some argument to it, the accessor must be a function. Thank you. So, passing a function, we just apply this function to both arguments. You might see some candidates for accessor functions over here. Right? See? How can we use this? For example, I hope you can see it even if it's a little, yeah, you have that, okay. So, let's say we construct a pair of coordinates on the screen. Let's say we are doing some painting on the screen, and we need a point on the screen that we deal with, that we paint to, for example, and we make a pair of x and y values. But the pair, what does this pair, 1024 and 200, what does that evaluate to? 1024, 200, it evaluates to a function. Thank you. It was a little less obvious, yeah? But it evaluates to a function, and we can call the function. We can call the function, and we have to give an accessor. Let's give it the FST accessor over here, which from 2 parameters, x and y, takes the first one. So this evaluates to 1024. And in the very same way, since we have hold on to our function, we can give it the SND, the second accessor, and we will retrieve the 200 that we kind of have stored in the function scope, in the closure scope, actually. And this is interesting because this kind of scope that we have here, this kind of scope that ensures us that this x is exactly the same as this x, is the only scope in JavaScript that you cannot compromise, which is not visible to anybody outside, not even to your developer tools. You cannot mess with this. With all other scopes, people can mess around and monkey patch and whatnot. This is the only scope which is safe. Now, you might say, currently, if I would have to create a pair, I would make an object, right? And give it an FST and an SND slot, a key, and then store it inside these keys, right? That's how we do it normally. Well, everybody can mess with your keys and change the values without you knowing it. But then how do you access this? Is it more difficult to access when you have the pair? Well, we do point open paren FST close paren, and you are doing pair.fst. How much different is this from this? Well, not much. You need to know the pattern, but you can just do it. And this pair is the foundation of all so-called product types. You might say object, a data structure where you can just store so many stuff, right? As much stuff as you have slots. Maps, for example. And this is it. Interestingly, it has very interesting characteristics which distinguishes it from other kinds of objects. Now, before we go into all the characteristics, let's go back one. This was for 2 parameters. You might see the pattern, how you can create this same for 3 parameters. Let's make a triple. I leave this as an exercise. So if you can make a pair and a triple and maybe a quadruple and a quintuple and a sextuple, how about an n-tuple, right? Can we just make an n-tuple for where we just say how many we want to have and we get them this way? Actually not. There's a nice implementation for this. In five expressions, no statements in the code, no variables, only expressions, in 5 lines. There's your challenge. Okay. How could you use it? Here's an example. Use it for a tuple. Usage for a tuple. Constructor for a tuple of 3 slots will return us in something that can be deconstructed with an array deconstructor. That's a little bit of JavaScript specifics here. So there's 4 things that come back. The constructor and 3 accessor functions, right? If we have this, we can use this constructor, let's say like so, person, no new. There's no class, no new, no this. Because class and new and this will get you in trouble. Right? As you know. No new. Person is a function. And we pass it our parameters just for creating a person. And if we want to, let's say, print the person, we say Dierk.firstname. Dierk parentheses first name. And that's it. And with an object or a map, you would have said Dierk.firstname. We just say the accessor function first name. And we have the value, the exact same value, uncompromisable. There is no way that you can possibly change this value. We have created an immutable class, and this is extremely valuable. I would say it's not arguably, you might claim that with the least modern JavaScript object freeze and object seal and so on, you might also be able to create true immutables in JavaScript, but it's actually difficult. This is the most elegant and safest way that I know of for creating immutables in JavaScript. A few years ago, before I went into JavaScript deeply, I asked one of our experts in JavaScript, can you make immutable objects in JavaScript? And he said, yeah, of course. Tell me, I want to know. He said, well, it's simple. How? He said, well, yeah, you make a JavaScript object, and then you don't change it. There you go. So, the constructions that we have built here leads to immutable values, not objects. Objects in the abstract sense of the word, not JavaScript objects. Well, and actually we are working, since all these constructions are lazy, there's nothing really constructed before you call the accessor methods. It's also extremely efficient. The modern JavaScript engines optimize this like crazy. Good. So that it was for the first part. Actually, my clock is not working. You have to give me advice when it's over. Maybe give me a hint after half an hour. Good. So that was every construction that you have in science, in computer science, has a complementary construction, which is then called the co-so-and-so. Like if you have a concept of a product type, then there is a co-product. And this is what we're going to, which has kind of the opposite characteristics. And same here. This is called duality of the category theory thing. Okay, here we go. So we start with a practical issue. We are a library author. We do API design. And we want to provide a function that takes an x and a y number, let's say, and it should give us back the division of x divided by y. But this might fail. If y is 0, this will fail. Our code might fail. We do something that might fail. We are trying to fetch by ID out of the DOM, but the ID might not be there, so shall we return null or undefined or divide by 0 error, whatever. All kinds of errors can occur. So as a library author, what do I give back if I have two things to give back? Either I have the right value, or I have an error message for you. A checked exception would be Java-like, right? There's no such concept in JavaScript that makes that safe. So therefore, and since we don't have these kinds of user-defined types, we have to put this in a construction that we construct ourselves, and we call this an either. So the idea is we would like to have a construction that we call either. It will be no surprise that this is a function. Okay. So it takes 3 parameters. First, whatever might evaluate to either the error message or the value that we actually want to use. Is that clear? We're calling the function. In this case, 1 and 0 would lead to an error message. Could be 1 and 1, and then it would be OK, and we want to work with the OK value. So either itself must give back, in our case, in the way that we use it, the correct value, the error message in this case, or dealing with the error message, and if this would be 1 and 1, it would give back the correct number. So the way that we are constructing this is, of course, with lambda expressions, since we are in the Lambda Calculus course here. Okay. So we are providing 2, handling the error case, handling the good case. These are my 2 functions. The error function that we provide gets the error message in, and we are doing something with the error message. For example, and let me go back. For example, console log of the message. Not a very good thing, but at least we don't even try to work with the correct value. Second is, We are just working with the result value. Let's say we're passing it into identity. It could be any function that is here. That's the principal idea. Now, we need to have some construction that captures either the good case or the bad case, right? We need two kinds of containers that contain this. And we call them left and right. The first one is the left value, kind of the error message. It's also conventional to do it this way. Second is the right value on the right-hand side, and also right. It has no political connotation here, right? Good. So this is what we want to do, which means we need to have a function called either that takes these three parameters. The either, the function for the good case, and the function for the bad case. We have no choice other than this. Good. Second, we need two constructors, left and right, that take one parameter and can be passed into either as the first parameter of the either. Okay, let's create one. Left with an x and right with an x. Done. Now, in the implementation of either, what can we possibly do? We have either left or right, an f and a g. We have three functions, and the only thing that we can do is calling these functions, right? So how about calling e with these two possible values? And then the e decides, if it's the left case and gets an f and g, it takes the f and puts the x into it. And in the right case, it takes the g and calls the g with it. That's it. You have just created a sum type, the either type, from scratch, no library, no framework, no NPM, no modules, nothing from scratch. Actually, yesterday in the afternoon, the workshop, we created all these abstractions from scratch. There's no dependency whatsoever for this code. And it works, right? I'm not doing this on stage here, but yesterday we could see that this works. If you call it with safediff 1 and 0, make a console log like so, and if you call it safediff 1, 1, the either will return the ID of the result, which is 1 in that case. Make sense so far? Now, we want to optimize. We want to apply Lambda Calculus. We want to apply algebraic refactorings here. Make the code even nicer. Who spots something in this case? Any idea? For the message, and this message, and this message, and this message? Well, this looks so utterly like normal JavaScript code that you might be surprised that you can apply Lambda Calculus to this. What can you do if you have a function that takes an argument and calls some other function with that same argument as the last argument? You can cancel it out. Eta Reduction. You can Eta reduce it. Second, you have a function that takes something, calls ID with that same thing. What can you do? Eta reduce, right? Whenever I ask, either the answer will be function or eta reduce. So if you do this, they just cancel out. Looks a little bit easier, right? Thank you. Can you spot more opportunities? Now it gets crazy. Who has been able to follow along until here? Everybody, thank you. Okay. In 1 minute, it will only be half of you. Because we just blindly apply the exact same thing over and over again. Do you spot another opportunity to simplify the code? Make an equivalence operation for shorter code? How about these? The last parameter and the last applied argument. We call this, the left hand is always eta reduced, right hand is function. So we call this eta reduced, thank you. Yeah, so if we do this away, it cancels out. Any more opportunities? We call this Eta Reduction, thank you. We cancels out. Now, by the way, what is this? We can alpha translate, we have x to x, which is ID, right? We put the definition of ID in. Either is just ID. If you're not totally surprised by this, then you haven't been paying attention, you know? We are discovering that these are the most basic data structures that you have in informatics, right? A product type and a sum type. Actually, all programming languages have product types, like data structures and so on, and very few have sum types, where you can distinguish between one or the other. You can get somewhat close with an, let's say, Java enumeration. Did I say that right? Yeah, an enum. But you cannot apply different methods to different enum values, like Monday to Friday or so. They always get the same method, so it's not quite the same. And if you have ad hoc polymorphism by subtyping, you can make subtypes that all have their own implementation of safediff, right? But you cannot really shield this from getting more and more subclasses at this point. Yeah, you can finalize, and so you can final on the class and so on. The same way that you do immutables in Java. But it's messy and cumbersome, and here you get it for free. And below all this is something as simple as ID and function application. Isn't that crazy? There you go. That's for the crazy scientist. Good. So, first we had pair and n tuples that give us true immutables. And now we are having either and maybe, which gives us null safe computation. And by the way, you cannot possibly forget to cover the error case. Let's go back. If you want to do something, if you want to do anything with the value of your computation, you cannot get hold onto the value, which will be passed inside here. You cannot possibly get hold onto the value until you provide also in handling for the error case. Otherwise, you will not get the value. You will recognize if you're not getting the value. There's no compile error because we don't have any compiler in JavaScript. But the very first try to hold on to the value will fail if you don't provide the error case. Now that is cool. That is useful in everyday code. You cannot possibly forget to handle the error case. Not handling the error case is the second most issue in all code bases. The most prominent error in every use case, in every code base is doing the wrong thing to begin with, right? Shouldn't be any program here at all. So anyway, that's it. Not handling the error case is shielding against not handling the error case is of immense practical value. But there's more. Just like with the pair and the triple and the n tuple, can we distinguish between good and not good, between errors and okay case? Can we distinguish between maybe 3 different options? Can we distinguish between an arbitrary number of options? And might that even be useful? Yes, you can. And here is an arbitrarily useful example that is a little bit involved, so let me go through it. This is from an actual test case, as you know from the asserts down here. By the way, the asserting I shouldn't say testing framework, because the framework consists of two functions. One of them is assert. The other one runs all the stuff. So also the testing facility, let's say, is totally built this way with algebraic data types. So what do we have here? We have a choice. We do have a choice of three possible choices, let's say. What this gives back, three constructors. There's three ways in which you can construct one of these choices, and a function that, when you want to have any of those, you have to provide a handler for all three, same as either. Clear so far? So what can you do? This is the real-world usage is you have a web shop, and in the web shop there's three payment methods. You can pay by cash in some way, you can pay with credit card, you can pay with an account transfer. These are the three options that we have for the payment method. Okay, and whenever we program how to pay, we have to provide functions for all three cases. We cannot just leave one way out. This will not work. So, how is that programmed? Well, we take this function and pass in the current payment that we're dealing with, which the web application has constructed somehow. Let's say in the test case, we are doing this manually, but it will be created somehow. So here comes our payment. Now comes first case, second case, third case. Okay, first case, cash. The cash handler does not take any parameters, or doesn't inspect them, because cash, you don't need any parameters, right? Good. So the amount that we want to pass out, or sorry, the amount that comes in, which is, this will be called with the payment method. What we do is we just create a string in our handling here, which says pay so-and-so cash, only for testing reasons. The second way, the credit card, will be used with an object, so this is object deconstruction, with a number and with the number of the credit card number, and the security addition to the credit card. So there's multiple things to consider in the handler. Now, once we have the amount, we say pay so-and-so with credit card so-and-so number, and here's the security code. So this would be any kind of calling of our transaction system which needs all three pieces of information. Note that in the handling, we are not bound that all three take the same kinds of parameters. They can have totally different parameters. As, for example, the payment, the transfer, has from and to as account numbers, how to pay stuff. Now, how does it work? If payment is of type cash, and we call pay with our payment, and give it the number 50, which is how much should be paid, this 50 will be called either here or here or here under the name amount. So it will be passed as an argument. But the other parameters in the beginning, like these empty one, has been applied here. So we have a partially applied function here, only waiting for the amount to start its work. And the result is pay 50 cash. Same for credit card, where we pass in an object with a number and a security. And if you call pay with a payment, note this is the exact same notation as here. This would be a general function. And it resolves to a totally different handling. And same for transfer. Does that sound useful? I would guess so. Now let's wrap up. what was rock solid and what was science in what we have done. We have created, with only the Lambda calculus and Lambda expressions, not even one statement, and no library, and no technology fanciness, only following the logic and the knowledge which has been created 85 years before by Alonzo Church and his colleagues. By applying this to today's code base, we created the best way of having immutable objects in your JavaScript code. We have created null-safe operations that work, you would say, polymorphically, but not with an ad hoc polymorphism through subtyping, but with a predefined, inspectable, recognizable polymorphism, what happens in which case. We need to cover all cases. If we do not cover all cases, it will fail. It will fail immediately. And all this with only expressions in the Lambda calculus in JavaScript notation. So if you want to follow along with what else you can do, that was only tipping the toe in the water. Yesterday we did much more in the workshop, and all the code of the workshop and much more. There's a treasure trove of stuff you can do, mostly unorganized and undocumented, but fully tested with test cases for everything. And example applications for games and for how to write Excel in the browser by applying this. Not remote controlling an installed Excel, writing Excel from scratch in 60 lines of code in JavaScript. Not every aspect of Excel, but the core that you can have functions in your various slots in your table data, which will be evaluated and that rely on the execution path through all the other functions, right? Functions that relate to functions in an arbitrary order and so on. So all this is stuff that I teach at university, but that you can just step into. It's free and open and comes with the do what you want but leave me alone license. Credits, if you want to hear more about this, Gabriel Lebec, under this Twitter handle, he's available, made an excellent talk, much better than mine, about Lambda Calculus and JavaScript, and even extended into more church encoding of Peano numbers and Booleans and all that stuff that we partly do at university as well. And an awesome talk. I can only recommend this. Second, I once put this challenge of how to write an arbitrary n-tuple with only a few expressions. After I found the solution, I didn't publish the solution. I created a challenge on Twitter and said, now this is the problem. Who can do this? And that was really interesting because from my followers, some of which are really high-profile software developers, they said, too complicated. The only person that can possibly do this is Daniel Dietrich. He's the author of Java slang, now called Waver, if you know this. And an all-around software development guru. And he got this, and he said, interesting, I don't have time for this at the moment. That was in the morning, 10 o'clock around. In the afternoon, around 3 o'clock, he said, okay, I have it. Well, I couldn't let go. Actually, I had an appointment, a meeting with my physician over lunchtime. I should have gone to this kind of doctor, but I canceled the meeting because I had to solve this problem. That was awesome, and actually he came up with a solution that was one line shorter than mine, pretty good. So, and since then we have this kind of conversation about this crazy stuff. Was awesome. So credits to him. And lots of credits to Gabriel Lebec for his inspiration. It's also very good. Furthermore, if you need any kind of support with this kind of code base or any other kind of code base, Raccoon gives you engineering, consulting, also on-site training. Maybe you want to explore in our JavaScript code, how could we improve? Well, call us, we come on site, and we work through your code, whatever. Second, next fall, starting with the fall semester next year, we will offer a certificate of advanced studies for web engineering at the University of Applied Sciences and Arts, which is Weiterbildungsthing. Yeah? It is aimed to be very high quality, high profile. We will produce very ambitious user interfaces in the web in an extremely efficient manner, much more efficient and much better quality than what you get with any of the currently known big UI frameworks. Based on solid principles and solid knowledge of the theory and of the technology, of Lambda Calculus and of JavaScript. This is like 12 weeks, not in one block, but like a little bit distributed. And every week there's 2 full days of work. So it's something, you know, it's certificate of advanced studies. Remember when Albert Einstein was in Princeton, he was at the Institute of Advanced Studies. So that's the bar. Okay. Do you have time for questions? The time's over? So do we have any very pressing questions at the moment? I wouldn't want to stand between you and your lunch. So it's dangerous. Any questions that we would like to raise in the audience? Yeah? Is that the question? Otherwise, thank you very much. I'll be around the whole day. Just talk to me.